Strategic leap, Polaris Spaceplanes to develop hypersonic transport solutions under €50 million defense contract. Date, March 1, 2025. Introduction. Polaris Spaceplanes, a German aerospace startup founded in 2019, has achieved a significant milestone by securing a contract from the Federal Office of Bundeswehr Equipment Information Technology and In-Service Support BAAINBw. This agreement, valued at under €50 million, aims to develop a cutting-edge hypersonic research vehicle furthering Germany's defense strategy and bolstering its capabilities in aerospace technology. The project centers on a fully reusable hypersonic spaceplane named AURORA, which is set to serve both military and scientific purposes. Project overview and objectives. The AURORA project envisions a 28-meter-long spaceplane that integrates the functionalities of a rocket and an aircraft. Its design allows for conventional runway takeoffs and landings while being capable of reaching hypersonic speeds exceeding Mach 5/6. 125 km per hour. The vehicle is intended to support a dual role, as a hypersonic testbed for defense applications and scientific research, and as a platform for launching small satellites when equipped with an expendable upper stage. Historical context and development timeline. 2019, Polaris Spaceplanes was established as a spin-off from the German Aerospace Center DLR, focusing on innovative aerospace technologies. April 2023, the company received its first BAAINBw contract to develop a linear aerospike rocket engine, successfully completing a test fire of the engine shortly thereafter. September 2023, Polaris launched the first of its MIRA demonstrators, achieving over 100 successful test flights with subsequent models MIRA 2 and MIRA 3. February 27, 2025, BAAINBw announced the contract for the AURORA project, marking the start of the design phase. Technical aspects and challenges. The AURORA spaceplane is designed to overcome several significant engineering challenges associated with hypersonic flight. One key feature is the use of an aerospike rocket engine, which has advantages over traditional rocket engines by maintaining efficiency across varying altitudes and speeds. However, aerospike engines have historically faced issues with cooling and manufacturing complexity. Polaris is addressing these challenges through the development of advanced cooling technologies and materials which could pave the way for successful hypersonic travel. The first successful flight of a vehicle powered by an aerospike engine occurred in October 2024, when Polaris conducted an in-flight ignition of the AS-1 engine on its MIRA 2 demonstrator. This marked a significant step in validating the technology and demonstrating its potential for the AURORA project. Strategic importance. The AURORA project is not just a technological endeavor, it represents a strategic leap for Germany's defense and aerospace sectors. As geopolitical tensions rise, the need for advanced defense capabilities becomes increasingly critical. The ability to conduct hypersonic flight tests and launch small satellites from a single platform enhances Germany's operational flexibility and responsiveness. Moreover, the success of the AURORA project could have implications beyond military applications. The vehicle's design may lead to a more cost-effective method for accessing space, potentially revolutionizing the satellite launch industry and enabling more frequent and affordable missions to low Earth orbit. Common themes across sources. Analysis of various sources reveals several common themes related to the AURORA project. All emphasize the dual purpose of the vehicle as both a hypersonic testbed and a small satellite launcher. The innovative nature of hypersonic flight technology is highlighted, particularly the advancements in aerospike engines and cooling technologies being developed by Polaris. Additionally, the ambitious timeline of 3 years for project completion is a recurring point, underscoring the urgency and importance of the initiative. Differences in source perspectives. While the core details of the AURORA project are consistent across sources, variations exist in the emphasis placed on historical context and technical challenges. Some sources focus on Polaris's previous achievements and milestones, while others delve deeper into the complexities of aerospike engine development and the startup's innovative solutions. For instance, one source may highlight the successful test flights of the MIRA series, while another might concentrate on the historical difficulties faced by aerospike technology. Conclusion and future implications. The development of the AURORA hypersonic spaceplane marks a pivotal moment for Germany's defense and aerospace sectors. It signifies a commitment to advancing hypersonic technology and enhancing national security capabilities. As Polaris transitions from the design phase to potential manufacturing and flight testing, the implications for both military applications and commercial space access will be significant. The successful realization of the AURORA project could redefine the cost efficiency of launching payloads into low Earth orbit, thereby influencing future investments in aerospace technology across Europe. Moreover, as NATO and European defense spending evolve in response to changing geopolitical dynamics, initiatives like AURORA will play a crucial role in shaping the continent's defense posture and technological landscape. In summary, Polaris Spaceplanes is poised to make a substantial impact on the future of hypersonic transport solutions and the aerospace industry as a whole, with the AURORA project setting the stage for groundbreaking advancements in both military and civilian applications. Counterintuitive information identified. 1. Cost-effectiveness of hypersonic technology. It is generally assumed that advanced aerospace projects, particularly those involving hypersonic capabilities, come with exorbitant costs. However, Polaris Spaceplanes aims to develop a reusable hypersonic spaceplane AURORA under a contract valued at less than €50 million. This challenges the perception that hypersonic technology is inherently unaffordable and inaccessible for smaller companies or startups. 2. Dual role of the vehicle. The AURORA spaceplane is designed to serve dual purposes, as a testbed for hypersonic research and as a platform for launching small satellites. This multifunctionality diverges from the typical view that aerospace vehicles are specialized for singular tasks, suggesting that advancements in technology can lead to more versatile solutions that maximize utility and resource efficiency. 3. Rapid development timeline. The ambitious timeline of 3 years to design, manufacture and flight test a complex vehicle like AURORA contradicts the common expectation that such advanced aerospace projects take decades to realize. This raises questions about current capabilities in aerospace innovation and project management efficiency. 4. Historical challenges of aerospike engines. Aerospike engines have historically faced engineering challenges that prevented their mainstream adoption, primarily due to cooling difficulties. The ongoing development of advanced cooling technologies by Polaris to address these issues presents a counterintuitive twist, suggesting that what has been perceived as a limiting factor in hypersonic propulsion may soon be overcome, potentially revolutionizing the efficiency of space vehicles. 5. Integration of military and scientific research. The AURORA project is positioned as both a military asset and a tool for scientific research. This dual-focus approach may seem counterintuitive given the often rigid separation between military and scientific endeavors in aerospace. However, the integration allows for shared advancements in technology that can benefit both sectors, implying a more collaborative future for research and defense. 6. Innovation from startups versus established entities. The success of a relatively young startup like Polaris Spaceplanes in securing significant government contracts and developing advanced technologies contrasts with the traditional belief that established aerospace companies hold a monopoly on such high-stakes projects. This shift suggests that innovation and agility in the startup ecosystem can drive advancements in fields once dominated by larger organizations. 7. Potential impact on European defense spending. The announcement of AURORA comes amid discussions about NATO's future and European defense spending. The assertion that innovative aerospace projects could influence broader defense budgets and investments challenges the typical narrative that military funding is solely determined by geopolitical pressures, indicating that technological advancements could reshape budgetary priorities. 8. Reusable spaceplanes versus traditional rockets. The notion that spaceplanes such as AURORA may provide a more cost-effective means of accessing space compared to traditional rockets, is counterintuitive as rockets are typically viewed as the standard for space launch. If Polaris succeeds, it could disrupt long-standing industry norms and encourage a paradigm shift towards reusable spaceplanes in commercial and military applications. These counterintuitive aspects illustrate the potential for significant shifts in aerospace technology funding and operational paradigms, highlighting how emerging players like Polaris Spaceplanes can challenge established norms in the industry. In the report regarding Polaris Spaceplanes and their contract to develop the hypersonic AURORA spaceplane, there are several important elements that may be overlooked by many readers. These aspects provide significant insight into the broader implications of this project, its technological advancements, and the strategic context in which it is taking place. 1. Dual role of the AURORA spaceplane. While many articles highlight the AURORA's capabilities as a hypersonic testbed and satellite launcher, the significance of its dual role is often understated. The AURORA is not merely a defense asset. It also has the potential to revolutionize scientific research by enabling advanced experiments in flight dynamics and propulsion. This dual functionality can lead to breakthroughs in various fields beyond military applications, including climate science, materials testing, and space exploration. The ability to conduct hypersonic flight experiments could yield insights that are crucial for developing next-generation aerospace technologies. 2. Historical context of aerospike engines. The report mentions the aerospike rocket engine being developed by Polaris but does not delve deeply into the historical challenges associated with this technology. Aerospike engines were first conceived in the 1960s. Yet they have struggled to gain traction due to difficulties in cooling and construction complexity. Polaris's advancements in cooling technologies and materials are pivotal. By overcoming these hurdles, Polaris could not only contribute to its own project but also reinvigorate interest in aerospike engines for future aerospace applications. This could lead to a paradigm shift in engine design, enhancing efficiency and performance for a range of aerospace vehicles. 3. Strategic defense implications for Europe. The context of this contract within Germany's defense strategy and its implications for European security are significant yet often overlooked. The project comes at a time of increasing geopolitical tensions and calls for enhanced defense capabilities within Europe, particularly in light of NATO's evolving role. The AURORA project represents not only an investment in technology but also a strategic move to bolster Germany's position in European defense. As Europe seeks to assert its autonomy in defense matters, the success of this project could serve as a catalyst for increased collaboration in aerospace and defense technology across the continent. 4. Potential for cost efficiency and space access. While the report highlights the AURORA's capabilities, it doesn't fully address the implications of its design for cost efficiency in accessing space. The ability to launch from conventional runways and the vehicle's reusability can significantly reduce the costs associated with satellite launches. This economic aspect is crucial, especially in an era where space is becoming increasingly congested and competitive. By offering a more affordable option for launching small payloads into low Earth orbit, AURORA could democratize access to space for smaller nations and private companies, fostering innovation in satellite technology and services. 5. Timeline and future phases of development. The ambitious 3-year timeline for the AURORA project is frequently mentioned but not critically analyzed. Rapid development in aerospace often faces challenges including technical hurdles, funding issues, and regulatory approvals. The implications of this timeline are significant as it suggests an urgent push to enhance national defense capabilities amidst changing global dynamics. Furthermore, the potential for follow-on contracts for manufacturing and flight testing is an important aspect that indicates the long-term vision for the project and Polaris's growth trajectory. The successful transition from design to operational deployment will be a key indicator of the company's capability and the viability of the technology. 6. Impact on European aerospace industry. The establishment of Polaris as a significant player in the aerospace sector may have ripple effects throughout the European aerospace industry. The success of the AURORA project could inspire similar initiatives, leading to a renaissance in European aerospace innovation. The emphasis on hypersonic technologies could attract investments and talent, fostering a competitive environment that enhances Europe's global standing in aerospace. This shift is particularly crucial as Europe seeks to reduce reliance on external aerospace technologies and develop its own capabilities in emerging fields. 7. Technological integration and collaboration. The report does not sufficiently explore the collaborative potential that Polaris's project could foster within the broader aerospace community. With advancements in hypersonic technology, there may be opportunities for partnerships with established aerospace firms, research institutions, and universities. Such collaborations could accelerate technological advancements and facilitate knowledge sharing, thereby benefiting the entire industry. The AURORA project could serve as a model for future projects that require a blend of innovation, research, and practical application. Conclusion. The Polaris Spaceplanes initiative to develop the AURORA hypersonic spaceplane under a €50 million defense contract is a pivotal moment in Germany's aerospace and defense strategy. While the key features and goals of the project are highlighted, the deeper implications regarding its dual-role, historical challenges, strategic defense importance, cost efficiency, development timeline, impact on the aerospace industry, and potential for collaboration are equally critical. Recognizing these overlooked aspects reveals not only the technological significance of the AURORA project but also its potential to reshape both the defense landscape and the broader aerospace market in Europe. 1. Innovative design and multi-role functionality of AURORA. The AURORA hypersonic spaceplane represents a significant advancement in aerospace technology due to its innovative design and multifunctional capabilities. Measuring 28 meters in length, it uniquely integrates the features of both a rocket and an airplane, allowing it to take off and land on conventional runways while achieving hypersonic speeds above Mach 5 over 6,125 km per hour. This dual functionality positions AURORA as both a hypersonic testbed and a platform for launching small satellites, which could vastly improve the efficiency of satellite deployment and defense operations. The vehicle's potential as a small satellite launcher is particularly notable. Equipped with a non-reusable upper stage, it could facilitate the placement of payloads into low Earth orbit. This versatility not only enhances its value for military and defense applications but also opens doors for scientific research and commercial use. The prospect of transitioning AURORA into a reliable launch system could redefine the landscape of satellite deployment, making it significantly more cost-effective and accessible. 2. Technological advancements, aerospike engine development. A key technological highlight of the AURORA project is the development of its aerospike rocket engine, which Polaris has been working on since its inception. Aerospike engines are designed to maintain efficiency across varying altitudes, a feature that traditional rocket engines lack. The historical challenges associated with aerospike technology, such as cooling and manufacturing complexity, are being addressed by Polaris through advanced cooling technologies and innovative material applications. The success of the AS-1 linear aerospike engine, which achieved in-flight ignition during tests aboard the MIRA demonstrators, is a promising sign for the AURORA project. This engine not only provides the necessary thrust for hypersonic speeds but also signifies Polaris's capability to overcome past engineering hurdles. The aerospike engine's deployment in a fully reusable vehicle like AURORA could lead to breakthroughs in propulsion technology, potentially influencing future aerospace designs globally. 3. Strategic implications for Germany's defense and aerospace sectors. The contract awarded to Polaris by the Federal Office of Bundeswehr Equipment Information Technology and in-service support BAAINBw underscores Germany's commitment to enhancing its defense capabilities through advanced aerospace technology. With a budget of under €50 million, the AURORA project not only signifies a strategic investment in hypersonic technology but also aligns with broader European defense objectives amid changing geopolitical dynamics. As NATO faces evolving challenges, the development of AURORA could bolster Germany's military operational capabilities and its overall position within the alliance. The ability to conduct rapid hypersonic flight tests and launch satellites could provide a tactical advantage, facilitating quicker response times and supporting various defense missions. Additionally, this project could catalyze increased investment in aerospace technology across Europe, potentially leading to collaborative advancements in defense and space exploration. 4. Future outlook and broader implications for space access. Looking ahead, the implications of the AURORA project extend beyond military applications to commercial space access. The design's reusability and efficiency suggest that hypersonic spaceplanes could offer a more economical alternative to traditional rocket systems, which often involve substantial costs for each launch. By providing a system that can routinely take off and land from standard airstrips, AURORA could democratize access to space, enabling more entities, including smaller companies and research institutions, to participate in satellite deployment and space exploration. The project's timeline, with a projected 3-year development phase, indicates a rapid advancement in this field. Success in the AURORA project could spur further innovation within the aerospace sector, inspiring new technologies and business models. The potential redefinition of cost efficiency in launching payloads into low Earth orbit may lead to a surge in commercial space activities, fostering an environment ripe for technological collaboration and competition on a global scale. Conclusion: the AURORA project by Polaris Spaceplanes encapsulates a pivotal moment in aerospace development. By focusing on innovative design, advanced propulsion technology, and strategic military applications, it highlights Germany's aspirations to lead in hypersonic technology. The project's success could transform both the defense landscape and the commercial space industry, making it a crucial development to watch in the coming years. 1. The Space Shuttle Program USA 1981 to 2011. The Space Shuttle was a groundbreaking reusable spacecraft developed by NASA. Designed to transport astronauts and cargo to and from low Earth orbit, it represented a significant leap in space transportation technology. The program was initiated in the 1970s, with the first flight occurring in 1981. The shuttle's ability to carry large payloads, deploy satellites, and service the International Space Station (ISS) showcased its versatility. However, the program faced challenges, including 2 tragic disasters, Challenger in 1986 and Columbia in 2003, which raised concerns about safety and cost. Ultimately, the shuttle program concluded in 2011 after 135 missions, paving the way for new space transportation systems. 2. Concorde supersonic airliner UK/France 1969 to 2003. The Concorde was a turbojet-powered supersonic passenger airliner developed jointly by British and French aerospace companies. It first flew in 1969 and entered service in 1976. With a cruising speed of over Mach 2, Concorde drastically reduced flight times, enabling transatlantic travel in under 4 hours. However, its operation was marred by high costs, limited routes, and the environmental impact of sonic booms. The tragic crash of Air France Flight 4590 in 2000 further diminished public confidence in Concorde. Despite its technological achievements, the aircraft was retired in 2003, highlighting the challenges of balancing innovation with economic and environmental considerations. 3. X-15 rocket plane USA. 1959 to 1968, the X-15 was a rocket-powered aircraft operated by NASA and the U.S. Air Force, designed to explore the boundaries of hypersonic flight and space travel. It flew a total of 199 flights from 1959 to 1968, reaching altitudes above 100 kilometers and speeds exceeding Mach 6. The X-15 program provided invaluable data on aerodynamics, propulsion, and human factors in high-speed flight. Pilots including Neil Armstrong and Chuck Yeager conducted critical research that informed future space programs, including the design of the Space Shuttle and other spacecraft. The X-15 set the foundation for subsequent hypersonic research and demonstrated the potential of reusable vehicles in aerospace. The recent contract awarded to Polaris Spaceplanes to develop the AURORA hypersonic spaceplane marks a significant milestone in the evolution of aerospace technology and defense strategy in Germany and beyond. With a budget of under €15 million. This initiative not only underscores the urgent need for advanced military capabilities but also opens new avenues for commercial applications in scientific research. The following predictions outline the potential future landscape shaped by the successful development of the AURORA project and the broader implications of hypersonic technology. 1. Advancements in hypersonic technology. The successful design and eventual deployment of the AURORA spaceplane could catalyze a new era in hypersonic flight. With its capabilities to exceed Mach 5, AURORA could pave the way for more efficient flight technologies, fundamentally changing the dynamics of air travel and satellite deployment. This could lead to the development of a new class of vehicles that combine the speed of rockets with the control and reusability of aircraft, drastically reducing the cost and time associated with reaching low Earth orbit. 2. Increased military capabilities. As hypersonic technologies are integrated into military applications, we can expect a shift in global defense strategies. AURORA's role as a testbed for hypersonic flight could enhance Germany's military readiness, allowing for rapid deployment capabilities and improved surveillance. Other nations may respond by accelerating their own hypersonic programs, leading to a new arms race focused on speed and maneuverability, which could destabilize existing military balances. 3. Economic impact on aerospace sector. The AURORA project's success could stimulate significant investments in the aerospace sector both in Germany and across Europe. As countries seek to bolster their defense capabilities, we may see an influx of funding into research and development of similar projects. This could create new jobs and opportunities within the aerospace industry, fostering innovation and collaboration among startups, established companies, and academic institutions. 4. Commercial space launch services. The dual-use nature of the AURORA spaceplane as both a hypersonic testbed and a small satellite launcher could reshape the commercial space launch market. Polaris spaceplanes could emerge as a key player in providing cost-effective launch solutions, potentially leading to lower prices for satellite deployments. This might encourage more businesses to invest in satellite technology and services, enhancing global connectivity and data capabilities. 5. International collaboration and competition. As hypersonic technology becomes more prominent, nations may engage in both collaborative and competitive efforts to advance their capabilities. Countries with established aerospace industries may form partnerships to share knowledge and resources, while others may seek to independently develop their own technologies. This could lead to international agreements focused on the responsible use of hypersonic technologies and the establishment of norms governing their deployment. 6. Innovation in propulsion technology. The development of the aerospike engine for the AURORA spaceplane represents a significant technological breakthrough. If successful, it could inspire further innovations in propulsion systems, enhancing efficiency and performance across multiple aerospace applications. Such advancements could also have implications for other sectors, including commercial aviation, where improved engine designs could lead to greener and more efficient aircraft. 7. Scientific research and experimentation. AURORA's design as a research platform will provide unprecedented opportunities for scientific experimentation in high-speed flight dynamics and propulsion technology. This could lead to major breakthroughs in our understanding of aerodynamics at hypersonic speeds, influencing future aerospace designs and applications. Enhanced research capabilities could also drive progress in related fields such as materials science, thermal protection systems, and autonomous flight technologies. 8. Regulatory and ethical considerations. The rise of hypersonic technologies will necessitate the development of new regulatory frameworks to address safety and environmental concerns in military applications. Policymakers will need to engage with stakeholders across the aerospace community to establish guidelines that ensure the responsible use of hypersonic systems. Ethical considerations surrounding military applications of such technologies will also come to the forefront, prompting discussions about their implications for global security. 9. Potential environmental impacts. As hypersonic travel becomes more prevalent, its environmental impacts will need to be carefully assessed. The development of sustainable technologies and practices will be crucial to mitigate potential adverse effects, particularly in terms of emissions and noise pollution. Future innovations should focus on balancing the benefits of hypersonic capabilities with environmental stewardship. 10. Public perception and acceptance. As hypersonic technologies transition from experimental phases to operational use, public perception will play a critical role in their acceptance. Transparency in the development process, as well as clear communication about the safety and benefits of hypersonic flight, will be essential in gaining public trust. Engaging with communities and stakeholders will help ensure that advancements in hypersonic technology align with societal values and expectations. Conclusion. The AURORA hypersonic spaceplane represents a pivotal moment in the intersection of defense and aerospace innovation. Its development will likely have far-reaching implications, shaping not only military capabilities but also commercial ventures and scientific exploration. As Polaris Spaceplanes embarks on this ambitious project, the ensuing advancements could redefine the landscape of hypersonic travel and its applications, ushering in a new era of aerospace technology.